what if I asked you to take a random real number from 0 to 1? How is that different? Well, first of all, what does it mean to be a continuous random variable? Let's ask ourselves that first. So, with real functions, we usually start by talking about continuous functions and only later consider discrete, discontinuous functions. I know, that's super thin. I didn't know. What? I just said I knew. So, here instead, in probability, most of the time, this is why we don't use the smartboard anymore. Oh, this is from my lecture 2 days ago. Okay, so for a continuous random variable, we start with a discrete random variable. So imagine you have a die. Of course, it has 6 results. 1, 2, 3, 4, 5, 6. All of these are in the sample space, S, and each of them is prescribed a 1/6 probability. Notice how the sum of all the probabilities over the sample space is 1/6 times 6, which is 1. Alright, now I want to ask you, what happens if we take a d20? I don't know how to draw an icosahedron, but you can imagine one is here in its place. I'm sorry. So you have 1, 7, 19, 25. So what happens if you take a d20? Well, the sample space now contains a lot more elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. And each of them is prescribed a 1/20th probability. So on and so forth until the sum of all of them is 1. Now, let's say you add so many sides to your die, it's essentially a sphere. So the probability of getting 1 is 1 over n, the probability of getting 2 is 1 over n, so on and so forth. The probability of getting n minus 1 is 1 over n, and the probability of getting n is 1 over n. Now, note something. There's an equal probability of getting any number here. And as n approaches infinity, you will notice that although the chance that you get an individual number is going to approach 0, the chance of you getting something somewhere is still going to be, 1. Now you can also normalize the results, like taking a dice that gives you 1/6, 2/6, 3/6, and so on, and you can have 1 over n, 2 over n, 3 over n, all the way to 1. Then, as n approaches infinity, you're suddenly looking at a continuous random variable that gives you some number between 0 and 1. That's what continuous random variables are. It's what discrete random variables approach once you have infinitely many possible choices. Well, uncountably many possible choices. So, how can we possibly talk about continuous variables the same way that we did discrete variables? Well, we can generalize a lot of things. First things first, we can generalize the expected value. Now, the expected value of a discrete function, or a discrete random variable, would look something like this. Well, I think it would be better to just write it as n. Okay, but now, what is it going to look like for Now, what is it going to look like for a continuous random variable? Well, just as a Riemann sum turns into an integral as the number of summands approaches infinity, this sum is going to turn into an integral from 0 to infinity of xi pxi. And this is no longer a function that has a bunch of blips of different heights here and there. It's now a continuous function akin to one, you would see outside probability. Now, this is a little bit easier to get your grasp on. But what's not as easy to get your grasp on is this. The expected value of, if you put g of x, for example, is going to be equal to the integral from 0 to infinity of g of x pi of x. Sorry. G of xi p of x dx. Now, how can we prove that? Well, that's something we're going to do next time because it's a lot harder than proving the same thing for discrete random variables. So, this is what a continuous random variable is at the end of the day. It's just what happens if instead of countably many values, you allow the variable to take on uncountably many values. And then things really start getting weird. So, that's it. Thank you everyone for watching, and next time we'll cover how to calculate expectation values for the expectation value of a function of a continuous variable, as well as the variance of a continuous variable.